a leisurely start. So it's with great pleasure that I introduce Professor Joe Chow from RPI. Joe has a master's and PhD from what's arguably the best EC department in the world, the Champagne of EC departments. My old institution, the University of Illinois, Urbana-Champaign. And he's actually, one of a handful of real scholars in the power area. So, if you haven't had a chance, you have any questions about power systems, you still have a chance after the lecture. He'll be leaving this afternoon. After graduating from Illinois, he was at General Electric for some time, and then joined RPI in 1987. And he's very well recognized for his work in a variety of areas in power systems, and transit and stability issues, and renewable energy, and PMU data. His work has been widely recognized formally, including a recent recipient of the IEEE BES Charles Concordia Award. Sure.
Thank you. It's certainly a great honor to be invited here to talk to you. And this morning I have an opportunity to speak to several graduate students, and it was truly delightful. Okay, I mean this is our future, right, Sean? Okay, I probably have way too many slides here, but let's see how when the time is up, I'll stop. Okay, so this is the university lecture mode. Now, how much time do I have?
Well, usually 50 minutes.
50, okay, I'll do 50. Okay, so we'll stop. When 50 minutes up, I'll just cut off. I have done a lot of work in different areas, but most recently I've been working on phasor measurement units. So I will tell you a little bit about phasor measurement itself and how you can actually use them. Okay, this is really a good time, if that's what your interests are, to actually study phasor measurement, because this is a new technology that has, this is a relatively new technology. Okay, so I'm going to give a standard spiel about our current ERC. I'll talk a little bit about how to actually measure phasors. Okay, and then I have a list of applications. These are the recent things that I have done. I have done earlier things, but I thought maybe we'll just talk about the recent stuff. So a little bit about the current ERC. So I'm part of it, and that stands for Center for Ultra High Area, and so on. And one of the two ERCs funded jointly by NSF and DOE, so the funding is 50-50. Okay, and there are two ERCs that are devoted to power systems. One is Freedom Center in North Carolina State University. This is the one in Tennessee, and we are the one who is doing wide area controls. We have over 20 industry members, and the center started 3 years ago. Okay, so we are actually in finishing the 4th year. Okay, actually 4 years ago. So this is the composition of the center. Kevin Tomsovich and Ilu Yu, they are respectively the director and associate director of the center, and it's this center at Tennessee, Knoxville. And we have a bunch of campuses. So I'm the RPI campus director. Professor Ali Abu, which is well known for his state estimator work, is at Northeastern. And Professor Greg Murphy, he's the department head at Tuskegee University. So this is what we call a partner outreach school. And we have 3 foreign university affiliates. Okay, and there. Okay, you see the Engineering Research Center is a whole package. Okay, what do I mean by that? It's a whole package because not only we do research, we also do outreach. We have summer camps every year. Okay, we have research experience for undergraduates both during the semester and during summer, and then during the semester. We have the industry program. We have and we also international collaboration. Okay, what does this ERC do? Okay, so basically what we're trying to look at is renewable resources. So the wind is very strong in the plain areas in the Midwest. Solar is very good in southwestern part of the United States, but the load center is on the coast. So one of the activity that we have is to look at transmission systems, renewable transmission, wide area control, okay, and demand response. So this is sort of a picture that we envision. The U.S. grid is divided into 3 separate ones. They are intertied with some of the DCs here. And the idea is to put in, so that what we like to do is, for example, be able to export the solar energy from the southwest to the east interconnection. And in particular, or even something more basic, trying to get wind power from Kansas and ship it to Chicago. Okay, so you need non-traditional power delivery facilities such as HVDC and even multi-terminal HVDCs. Another part of it is that when you do wide area control, you actually have to have measurements. So the measurements that we are working on now is based on the Phasor Measurement units, and this is a picture as of October, so a year and a half ago. This is where you actually have locations of Phasor Measurement units. And so you have issues such as data quality, communication network, and how do you actually put the data into control room, okay, so that the operators can use it. And of course now there's over 1,000 PMUs and maybe even more, okay. And so this is sort of an animated picture of looking at various aspects of our work. So we have PMUs and FDR. FDR is the frequency disturbance recorder built by Professor Yilu Liu, first at Virginia Tech. Of course, the whole operation is now in Tennessee. And these are the equipment that will plug into a wall outlet, and it will measure frequency and voltage. Current doesn't make any sense here because you're just measuring the circuit. So these are our measurement equipment, and then there's the communication network, internet, actuation. So you have what can we control? For example, flexible AC transmission equipment, responsive load, and then HVDC system. And in terms of generation, we have solar PV, wind, conventional generator, and in terms of the newer kind would be responsive load. I think this is a water heater. And then storage, battery storage, perhaps even involving electric vehicles. And essentially, this is a picture of wide area control. Okay, so we are moving towards that. I mean, we are moving a little bit slowly but deliberately towards that. It's a big problem. Okay, so what are we really looking for? Eventually, 100% renewable penetration, okay? And we do need a 60 hertz reference somewhere, because otherwise all your appliances won't operate correctly. Maybe those will be our hydro generators, so it's really 100% renewable, okay? And frequency response will be an important aspect of it, and I think demand response and all the regulations reserves are all aimed at that. I won't be talking about how do you actually do frequency regulation on wind turbine. That's a topic for another day. More pertinent to today's talk is, let's look at PMU data, smart meter data. First of all, is it big data? No matter what data it is, we need to get the most information out of the data. And then there's the control part, okay? And then we also have economists who works with us to look at economics and optimization. We actually lost the guy, so never mind. That's a long story. So first of all, I'm going to talk about phasor measurement. Okay, so this is a 3-phase power system with A, B, and C. And then this is an ideal plot. You have normally 50 to 60 hertz. And B is behind A by 120 degrees. So from here, 120 degrees is 1/3 of a cycle. Okay, and then C is further 120 degrees behind. Okay, So, so how do we actually measure basic quantities on a power system? What does the ISO use? Okay, so you have basically still a voltage and a current measurement. You use potentiometer, these potential meters, transformers, and you have these current transformers, and you have analog circuitry. So the analog circuitry over here is just computer voltage magnitude. For the line current part, you seldom communicate the line current value, but you actually communicate the P and the Q on the line. Okay. Now, what happened is that these things are sort of, you measure it and you send it up to the internet, and this is called called ICCP, Inter-Area Control Protocol or something. And basically, what happened is that this data is in the network, and all the control center has to do is to download specific data from the network, and they're going to run their state estimation and so on. Now, what happens is that they are measured every 2 to 4 seconds, or sometimes less frequently, and they came from these remote telemetry units. And remember that they are all asynchronous data, and you have no idea how good the value it is. So there could be some data that stay there for hours and not changing because, hey, the thing isn't working. Okay? And so the beauty is this, that if you have a new data, you go there and you substitute it, you kick the old data out. But the data that's there have no timestamp on it, so you don't really know when the last time it was refreshed. Now, but the power system engineers are pretty clever, okay? And you ask, how can you do this? Yes, you can do this. Because voltage, P and Q, they don't change abruptly. Their values may be slightly different from the earlier, but this doesn't really change 50%, okay? And as a result, you can do state estimator. So the premise with the state estimator is that every measurement will now have the true value plus some kind of uncertainty due to many different things, measurement itself or the time difference, okay? So this works very well, okay? Now, what is a phasor? Okay, this is a little bit different now. So you have a now sinusoidal signal, just like 160 hertz. So you measure, you describe this signal by amplitude A, and you also, when there's a peak, so this is where you define the phase. So the description is that A is the RMS value, so it's the frequency plus a phase shift. Okay, so the frequency is simply a frequency that everything is moving around at the same speed. Okay, and so you don't describe that in general. You just provide A and V. Okay, and and of course most of the phasor measurement unit will actually put out a frequency, but this is you don't do a frequency for every channel, but you do a frequency for all the channels. Okay. Now, one thing is that a phasor, or the positive sequence value of the phasor, cannot be computed instantaneously from single data points. So you cannot take a snapshot of phase A, phase B, and phase C values. Those are real values. They are not complex values. Those are real values. You cannot go and take those values, compute a phasor. That doesn't work. So, oh, sorry, wrong direction. And also the phasor is you can represent it by amplitude of phase or the real part, imaginary part. No, that's both are fine. They are both acceptable for phasor streaming. So this is the very first PMU unit in Virginia Tech. Did you see these?
Yes, I did.
Okay, you saw this. Okay, so courtesy of Professor Arun Faki. Okay, so I think those are the 486, these 8 terminals of. But anyway, so what really happened, the real story was this. They actually put this equipment out in AEP, American Electric Power, and it didn't work. You know why? because what happens is in the lab, they forgot to do shielding. So if you put it in the wheel substation, the noise basically overwhelmed the system. I mean, of course, they fix it quickly, put some shields around. I mean, the utility actually knows what's going on. Put them in a box. So why can you not compute phases instantaneously? Because this is the actual measurement of three-phase current and voltage during a generator a low rejection test. Basically, you open the circuit breaker, and then we do the calculations. Okay. So what happens is you can see this is a hydro unit, and you can see the current. It's sinusoidal enough, but it's not really perfectly sinusoidal, and the amplitude in different phases are not the same. Okay, and so is the voltage and so on. And and there are 48 points per cycle. So this PMU actually sample at 2.88 kilohertz. Now, this is a test. This is a low rejection test. Okay, basically, you pull the circuit breaker. Now, when you pull the circuit breaker, does all three phases open at the same time? No, you can't, because you will create a lot of spots around, right? Or little gap, and then you still have voltage across it, current across it. So what happens is that circuit breakers can only open at zero current crossing, because then you can open it safely and so on. And what happened was that this circuit breaker was actually damaged. So this is the point where you try to open, it was not successful. So it continues through this. And then here, there's another part they try to open, it didn't work. And then you have go on to the next cycle, and here you see, zero crossing, open successfully. Okay? And then in between the voltage, you can actually see spikes. Okay, so after what happened is that we didn't know what's going on, so we actually recorded this, and I analyzed it and showed it to the station engineer. And the guy looked at it, he wasn't really happy. So after we did the test, he asked people to open up the circuit breaker and found the broken pieces of it, and he replaced it immediately. Because the problem is that if the circuit breakers are not open properly, if you have a short circuit right next to a generator, it's going to damage, it's going to ruin the generator. Okay, so what happens is that now how do you calculate phasor? So what happened is that you actually have to do real digital signal processing. Okay, so you take an analog waveform and you sample it at regular intervals, and then you actually do a FFT on it, or DFT. Okay, and then what happens is that now over here I illustrated with one cycle, but normally PMUs would either use 2 cycles or even 4 cycles. Okay, so phasor measurement has an inherent delay in the signal processing part of it. Okay, so this is not an instantaneous process. And so the story goes is that, so General Electric implemented that, okay? And then they, because eventually this, and what also happens is that this is about 1980. So the relaying community has a decision to make. Are you still going to go with all analog relays, or are you going to go to digital? Because now the microprocessors are a little bit cheaper, you can actually do one affordably. So apparently they decided that they were all going to go digital. So all the relay manufacturers are going to go digital, okay? So one of the things that people were trying to do is to do, because the microprocessor in those days was still expensive, so they would do iterative discrete Fourier transform. So what happened is that if you have a new data point here, what you can do is that you can drop this data point value, do a phase shift, okay, and put in the new data point. And then what General Electric found was that something was screwy after a while. You know what happened? The phasor would not be accurate. The truncation error, right?
I'll question here. Since the power signal is only 60 hertz, right?
Right.
Why you sample so fast or not using the microscope?
Okay. Because you see, this one is, so if you use 2.88 kilohertz, now people are using 5.6 kilohertz. They're even double the frequency. So people have decided on that 48 points per cycle is good enough for you to actually do this calculation. Okay? So internally, this is internal signal processing. They are very fast.
Yeah, I know it's very fast. It's too fast.
And that's still not too fast. It's not too
It's
fast.
only about 120 the sampling point would be enough.
Well, okay.
Yeah, but you need more, who's asking?
Huh?
Oh, so you need more, as more data you have, the more precision you will get. So actually nowadays, if you have even more data, more sampling rates, the precision of the phasor with respect to the real life is going to be better.
Oh yeah, I know it's better. Sometimes if you oversample signals, sometimes have a problem, right?
No. This is simply a computation on the basic signal, and then, of course, what happened is that you do have the downsample later on. Okay. So they found out that it was a problem with the truncation error, because the truncation error is a nonlinear noise, right? So after a while it was not accurate. So now they don't care. They just they don't do the iterative process anymore. Microprocessors are cheap. So this is what happens with in a PMU. So you take the signal, you do the anti-aliasing filter. Okay, so this is still analog. And then you actually have to do an A to D converter. So what happened is that, again, power people are pretty cheap. So you basically multiplex. A to D converter, there's only one. Okay, that can be the most expensive component in this thing. So you sequentially sample all the channels. And then you actually have a GPS signal to timestamp the measurement. Okay, and this GPS signal, in the US is about 2 or 0.2 microsecond in accuracy. Okay, and so what happened with this GPS signal is that GPS will put out every second on the second a pulse. So all these PMUs will do, all these antennas will do is just pick up that second, and then it's going to use a phase lock loop type of phase lock oscillator. So it's going to generate all the sub-second points for the A to D to do the sampling. So you have a decimation filter. And then you have a single phasor estimator, basically the FFT stuff, okay? And then you can do a symmetrical component, so because you do have phase A, phase B, and phase C. And most PMUs measure all three phases. Another issue here is that you actually have to estimate the frequency. Power system rarely runs at exactly 60.000000 hertz. It's more like 59.997, okay? So anytime you have a slightly off nominal frequency, when you do phasor calculation, you'll find that it imposes a second harmonic on the magnitude. So what happened is that if you have 60 hertz and you do a complete cycle calculation, it's like working on a circle. Okay, but if you have an off nominal frequency, then the phasor will trace out an ellipse. So as the ellipse goes around, its amplitude, okay, changes, and it changes. It's a second harmonic on it. Every cycle, you actually see one of these things going through. So this is what Daniel did when he was here. Professor Data actually built a PMU simulators in software, in Simulink, that you can put in all kinds of test signal to it, and it works like a real PMU. Except it's all in a computer. Okay? And then you reformulate the data and send out the signal. Okay? So on the surface, what can you use the phasors for? You can do flow calculation. Okay, so what happened is that if you measure the voltage phasor here and the voltage phasor on the next bus over, remember now the voltage is not just the magnitude, it's also the phase. So you can easily calculate the flow between the two. So all you have to do is V1 minus V2 over the reactance. That's pretty easy. Now, the other option that you have is that, and this is more common, is that if you put a PMU on this bus, in addition to the voltage phasor, you're going to measure all the currents that's going out. Okay? So what happens is that if you use this voltage phasor and this current phasor, you can calculate this V2. So you will make the next bus observable. This is not so easy to do when you have just an amplitude over here. Okay? And this is a direct calculation of the next bus over, so it's not a state estimator solution. So people will call that this is the linear state estimator because you don't require any iterations. This scheme works if you have very, very accurate phasor measurement units, okay, which we found that is still not quite the case. For people who are interested in dynamics, then you can actually look at oscillation. So you have some kind of a transmission path from one end to the other end, bus 1, bus 2. And you have a disturbance on it, okay, and you measure the frequency here and measure the frequency there. Now, we are not talking about generator angles, okay, because in general, PMU units are not inside the generating station. If you look at the frequency difference, that's actually, the inter-area oscillation between the 2 points. Okay? They are not as good as rotor oscillation, but they're good enough. Okay? And there are 30 samples per second, and this oscillation is between 0.25 to 3 hertz, so there's plenty of bandwidth to see that. Okay? We are in Florida, right? So this is an event in Florida. Okay? I don't know how many of you lived long enough to actually remember this. 2008, there was a relay that misfunctioned down on a nuclear power plant, and something really exciting happens, after that, right? I mean, a few people lost power, but the point, I think, is this: this is actually phasor measurement data from PMUs. Okay, so the event is that the nuclear power plant tripped, and what happened is that as a result, a lot of loads were tripped, and they actually tripped more loads than power, than generation. So what happened is that in Florida, initially the frequency actually rose just because of you have more generation than load. And lo and behold, and this frequency rise is propagating to the rest of the system. From Florida, you go to the first part that we have is Tennessee. So that's the West Tennessee and the East Tennessee. And then after that, it's going to be Manitoba. Now this is all the way to Minnesota and to Manitoba. Okay. And then after that, it went to Maine. Okay, so this is the Orrington unit, which is right across from New Brunswick. And of course, these are oscillations, so anything that goes up has to come down, so you have these really nice oscillation going around. Okay, and the next one is actually this is actually using the Virginia University of Tennessee equipment. Let me see, I can play this. I have to move it over here. Now, before I start, okay, the disturbance is going to start from here. Okay, so green means everything is roughly around 60 hertz. Red means that you are over frequency. Blue means you are under frequency. So you will actually see this disturbance spread out. Okay, and I think this is running in real time, or maybe a little bit faster than real time. Where's my... So those are the absolute value of the frequency. The pointer is the average. Okay, so you can actually see that disturbance did go all the way up to Maine and they all go all the way up to Manitoba. Now, the eastern system is really complex to analyze. You know, as I, for example, I'm not sure that I can do it. But one thing that is interesting to observe is that you can think about the eastern interconnection as a big mesh down here, but you have three things that sticks out: Florida, New England, and Manitoba. So anytime you have things happening around here, these three areas were going to be shaking, you know. Okay. Now, of course, the oscillation in the eastern system are well damped, but the ones in the western system are not. So what happens is that this is an event that was recorded. Now all these dirty stuff here is basically oscillations. It's a 0.578 hertz oscillation, but it's being packed together. So this is like about 4 minutes or something. Okay. So what happened is that I think some equipment got tripped and so on, and the system went into oscillatory mode. So this is the angle difference between somewhere in Montana versus like Washington, Seattle. Okay, so that's the oscillation, the angle between those two. And this is I think I didn't advertise it. This is the frequency difference between the two ends because we don't have the machines. Now this is, Sean, this is what we did. You know, we took this and get the quasi-steady state out of it. Okay, subtract from it, and we got these really nice oscillations. And the really interesting thing is this, that you can actually use the speed and the angle to create a Lyapunov function or energy function. And when you put in the right inertia and stiffness parameters, you can actually show that this is an energy function, and when you add them together, all these oscillations disappear. The energy function looks like this, and everyone so why it got kicked up because something else happened in the system and going through like this. Quite nice. Okay, so let me talk about all the different applications that we have. Okay, first of all, state estimation. So this is Luigi actually liked this. This is Luigi's picture. Okay. So basically, this is what state estimation does, you know, and this is the conventional part scatter, and you do contingency analysis, optimal powerful. And now the question is that if you have single phasor measurement, how can you use it? So there are obviously two ways that you can use state estimator. You can actually take the data in here and make the conventional state estimator more reliable, or you can actually use the data itself, but only estimate the high voltage backbone of the system. And this is what we did. Okay? So this is the difference between the scatter recording and the PMU recording of the voltage magnitude, and this is a bus in central New York. And you can actually see that, hey, there is an oscillation here, right? Even though it's one cycle. Whereas with the scatter data, you just, something happens, you have no idea, right? So we are looking at the the phasor only state estimator, and as usual, at the observability, how many PMs you need, how about loss of PMU data, okay, and the benefit of this phasor state estimator is that we know that we don't need to put a PMU at every major substation. We can actually calculate the ones that we don't have. In particular, we like to know the output of generators. But in New York, the generating substations, the connection to the grid is normally owned by the generator owners, and they are not obligated to put PMUs on it. So what you have to do is in the neighboring bus, you actually have current phasors looking at it, so you can actually calculate this. Okay? And for those of you in control, you can actually think about dynamic state estimation. There are enough of a bandwidth so that you can go and calculate the internal states of a synchronous machine. And after that, you can do model validation and so on. So extending visibility, we already talk about that. You know, a PMU can go from this bus and see this bus, and this is a non-iterative linear state estimation. And I think this is one of the papers published in. And Karimi is actually the head power electronics designer for Boeing aircraft right now. So, I mean, these people, you thought that after they start working for the industry, you'll see them back, but you see them often. So he was the chief investigator of the battery problem in 787, the Boeing 787. So not going into details, it's almost like that if you can put PMUs on 1/3 of the buses and measure all the currents going out, you'll probably have full observability of the system. One thing that we found early on, and that's the nice thing about people giving us PMU data, is that we've actually found out this curious thing about the phase of these PMU measurements will, from time to time, go do something like this. I mean, someone who's experienced at that would actually know, okay, it shouldn't happen, okay? And so we were wondering what it's about, but then the guy at AEP told us that it always jumped like 7.5 degrees, 15 degrees, 22.5. It turns out that if you look at one cycle with 48 points, if you miss a point, it's 7.5 degrees. So somehow the timing circuit of that PMU will screw up, okay? So, so we promised the guy that we are actually going to do something to back this jump for him so that he doesn't have to do it manually, okay? So this is what we end up doing, okay? And then further on, you actually have issues like, wrong phase connections, so you got bias, you can have synchronization error, okay? And even instrumentation cable, sometimes the CT is very far away, and if you have a long cable, and then even the filtering algorithm will introduce a little bit of delay for you. So how do you actually account for that? Oh, so this is what I meant. These are jumps, okay? All these, but of course, this is in some really old PMUs that have this problem. Newer ones don't seem to have this problem. So the idea is actually very simple, okay? So what we have is that of all the PMUs, they are connected with what we call redundancy. This is a redundant bus because it doesn't have a PMU, but it can be observed, it can be calculated from this end because it has a voltage and a current measurement. It also can be calculated from another bus, the voltage and current calculation. So you can actually calculate this bus from two different sources. Okay?
You really know the reactance?
Yeah, the reactants are actually quite good. I mean that we are now at a point where the reactances that we see, well, we were at the very end, we were looking at 1% error in the phasor, in the adjusted phasor data. So the 1% error could be truly due to the fact that there's still inaccuracy in the phasor, but or the line parameters. But when you get down to 1%, it's difficult to correct. Okay. So the idea is actually very simple. For every PMU that you have this kind of connection, you will introduce this phase shift at all the channels, because this is the way that the phases are computed. Because remember that when you see a phasor, you will see a magnitude and a phase. A phase is natively computed in the PMU, and it should be calculated accurately, even though the magnitude is scaled improperly, right? Because if the amplitude is high, it's like this, amplitude is low is this, the phase is the same, okay? So this is, and then you can do all these, okay? And the other thing we can do is look at the line currents, okay? Line currents are a little bit more difficult to do because voltage measurements, it's a tight range. The line currents, depending on the operating conditions, it can be high, it can be low. And especially at low current values, is really out of the region of linearity of these, okay? And so in case we actually have situations where line currents is measured on both ends of the lines, we can actually do the calculation. So here is simply putting in a scalar to multiply this, okay? So I'm not going to go further on this, but to that we actually going to have an opportunity to deploy this software on real power systems. So we actually have data from New York and New England, New York now including New York City and Long Island, okay? 3 voltage levels, those are high voltage levels that we have. And then the neat thing that we can do is that we can connect New York and New England as a single state estimator solution, okay? The reason why we can do that is that we can actually have, because they have PMUs, they are looking at each other. Okay, so we can actually form the redundancy. Now, we'll try to put in a plug to justify the angle bias correction, because there are portions of the network where we have so many generators in a small area. We actually have neighboring buses that had a very small angle difference. Okay, and so the angle difference is on the order of 0.08 degree, and the native accuracy of the PMU is about 0.1 degree. So you can easily have this in the wrong direction, and you actually have the flow going from a substation back into a generator instead of generator go out to a substation. Okay, and the total vector error is normally less than 1%. And at some point in time, we are going to be able to provide this on Grid Protection Alliances in the single phasor business. They actually produce a open PDC. This is phasor data concentrator. So this is the box that collects PMUs from different sources and manage that. Okay. Now, the next topic I thought it would be interesting is to actually look at some recent work that I have been doing with Professor Meng Wang. She has a background in signal processing. So I mean, lots of people have studied that, and they decide that the PMU data is really sort of the big data analysis for power system. You know, you have in Europe you have 50 points per second. In US mostly 30, but sometimes 60, and you are recording, you know, throughout every second in time, and then so you will have gigabyte and terabyte per day. Okay, and New York, for example, have 40 PMUs, and New England have roughly the same. Other places have more, and obviously we have used previously these things. Look at disturbance triggering location, not so much as assessing the severity of the disturbance because we don't see that much, and ultimately trying to avoid cascading failure. So of course, big data is a buzzword. So do we actually have a big data toolbox somewhere? And if you know one, let me know, okay, but maybe someone is secretly building one. So this is sort of a picture of PMU data, okay? So what we have here, down here, just think about space. It should be really 2-dimensional, but I only have 1 dimension. So you have PMUs in New York, New England, PJM, and other guys. And then over here is time, okay? So this is like this is the newest time, and this is the oldest time. So that when new data comes in, it's going to push the data off on this side. So what we want to really propose is the following. Now, when you really lay out this PMU data, what you can see is that you have missing data. Okay, for whatever reason, you know, you're too cheap to pay for a wide bandwidth communication link, and when congestion comes, you don't have data. Okay, you could have bad data. Okay, you can have disturbances. Okay, and you can maybe under cyber attack. Okay, so of course there are many other possibilities. But these are the ones that we're working on. So in terms of disturbances, it could be disturbance 1, disturbance 2, and disturbance 3. The key thing that operators are worried about is that to make sure that these disturbances are not really related, it's one after the other. This is the problem with cascading failure. Okay, you know, this line trip is not because of the fact that there's a line trip over here. And if you do, you better be really, really careful, because this could be had a wider impact. Okay, so one of the things that the power engineers have to really do is to make sure that before you use the data, it has to be very good and reliable data. Otherwise, you are taking control actions based on lousy data or bad data. That won't fly. So I say it's like housekeeping chores. If you have missing data, can you fill in the data? Bad data, can you correct it? Cyber attack, can you find it? Can you check on system oscillations? And now lots of people are doing that. So this is one of the big applications. If you alarm on disturbances, find out what disturbances. And lastly, correlations between disturbances. And as a result, possibility of cascading failure. And the big question that we want to pose is that, do you want to all those do these things all really, really separately, so everything has a specialized approach? Or you want to do it on a single platform? Okay. And one thing that we have done up to now is single channel processing. So you take one channel at a time, trying to squeeze as much information out of it, and then you go to the next channel. That's not very wise, I think. So this is an old recording that we have. Okay, there are 3 or 4 events. They're all the same event, meaning losing ISO New England, loss of 1 pole of the, this is the HVDC from Quebec to close to Boston. Okay, and you can see that these events. So in the old days, we were looking at that channel and figure out what we can do with the channel. So now it's different. Okay, so what we have here is that this is a disturbance on the New York system. These are the current amplitudes, and these are the frequencies. Okay, and you can see that most of the frequencies are almost the same, and except for this one, because most of these frequencies are from central New York. This one is actually from central New York, actually, like Albany, where I live. Okay, and this signal is actually from Niagara Falls, the power plant over there. Okay, and so what happened was that this was an event coming from New England, going through the central part of New York, going to the western part of New York. So you can actually see that this red curve is a little bit slower than the rest of the curve. Okay. Now one thing that you have to know is that power system is an electrical circuit on a bigger scale. Okay. There are inherent relationships between all the different quantities in the network. Okay, it's this, these relationships can change from time to time, but at any point in time, for maybe 5 minutes or so, they are actually quite regular. So what and one thing that we find out is that if you try to put this data as a data block, it's a big matrix. If you compute the singular values of that, you'll find that 80%, 90% of your singular values are very small. There's only a few big singular values. And that means that there is a dependency on all these channels. So this work with Professor Meng Huang. And previously, other people have actually exploited this. And in particular, this is a paper from Texas A&M. It's P.R. Kumar. They actually recognize this, and they use principal component analysis. So we use singular values. Same idea, but we may be a little bit cheaper then. So and then what we end up looking at is that long time ago, there's this thing called Netflix problem, because Netflix gave out a price of $1 million for someone to come up with an algorithm that would beat their algorithm by 5%. You see, what Netflix wants to do in the old days is that they want to keep selling more movies to their subscribers. And it's important that you recommend movies to the subscriber that they would like to see, okay? And so they, every time after you finish watching the movie, you give it a rating. Okay, so suppose that they look at this, Sean really likes to watch action movies, okay? And maybe his wife likes to watch romance movies, So they will have these things all tagged for you. You don't know about it, but they know, okay? So they ask the optimization community to develop algorithms that will beat their own in-house algorithm. And I think they predict that that someone may be able to do it in 5 years. But what happened is that some guy from Sweden or Denmark had an algorithm that beat them in 2 years and collected a cool $1 million. So what happens is that, let me just do this. So one thing that we can actually do this is to do data compression. So we can take each of the blocks, compute the singular values and singular vectors, and only keep the ones that are large. So that's kind of obvious. Okay. So for example, the data compression. Okay. So if you just keep, you start from this, you keep one singular value, this is what you have. So you miss the frequency from Western New York. If you do two frequencies, two singular values, hey, you're almost there. Now, how come? Oh, okay. Meng likes to do this. Okay. So missing data recovery. Okay. How do you do this? You have, and just I have to apologize because right now we are still trying to keep the previous value. If we don't have the present value, keep the previous value. But you can be a little smarter. You can actually interpolate, right? You got this value, and then the future value is here. You draw a straight line, you get this. So what happened is that the optimization people are doing great things on this. Okay. So what we have is that we have low-rank matrices. So if you are missing data, can you fill in the missing data and still keep the low-rank condition of the matrices? Okay, so there's this nuclear norm minimization stuff. And then there's also now the algorithm that we try is the singular value thresholding and the information cascading matrix completion. So of course, when we do experiments, we actually have all the data. So we selectively drop data from this. Okay, and for the wheel matrix, it actually has a nice singular value plot like this. You know, after the fourth singular value, the rest isn't worth keeping. Okay, and then we have 6 PMUs, 37 channels, and you know this is the central New York system. Albany is right here. So what happened is that Meng actually dropped data like this. So she has this parameter tau, right? Okay, so 1 to 9. And what happened with PMU data is normally you just don't lose a data point. You lose several data points. This is the congestion issues, right? So you will lose a bunch of data points. So this is the experiment that you try in terms of reconstruction and so on. So the blue curve is a continuous curve, and then the X is the erasure estimation. You can see it quite well. Now it turns out that this is the error estimate of the algorithms. So this is the how say 0.2 means that you lose 20% of the data. Okay, the recovery error. Okay, and the ICMC is even more impressive. You lose 30% of the data, you are still doing okay. Okay, the error is small. Okay, now of course we don't. This is not our own invention. We're just using algorithms developed by other people. And I mean, this is matrix completion is probably a very hot topic in data mining stuff as well. Oh, data substitution attack. So the idea here is that, now of course, after Vince Poor published his paper on the data substitution cipher attack analysis, data substitutions are the ones that you cannot detect by doing state estimation. Because someone does not just change one data point. It changes a set of data points so that they still keep the consistency. And Sean, if you want to leave, go ahead. Okay. And so the idea here is that if you have a measurement on V1 and V2, if someone go and change your current measurement by some amount that depends on the impedance of it, so by make sure somebody grab his jacket. Want a jacket? If you use this measurement to calculate this point, you actually have the same value. So a state estimator would thought that, hey, this is good data. Okay, so and then there are various schemes for doing that. So you have so one of the things to do is to make sure that you completely protect certain critical PMUs that cannot be penetrated. Okay, so that's one way. Now, for us, our assumption is very simple. That they can actually manipulate data, okay, and they can manipulate the data over here, manipulate data over here. But the key thing is that if the attacker completely takes over your system, there's nothing you can do. All the erroneous data look pretty good, right? But so the key thing is that if you have the system, most of it is okay, and you have pockets where people will attack you, and not on a consistent basis, okay? They can't do it at every point in time. Then you actually can formulate it as a matrix problem. It's a mathematical problem, okay? This is the measurement with corrupted cyber attack data. What you want is that you want to have a low rank matrix. You want to have a column sparse matrix like this. Okay, and then you have, this is basically the network relationship in the for the data, and there's always some noise. Okay, so the idea that you do know is that you know this measurement, which is M. Okay, you know the relationship between the node, which is the W matrix. Can you go and identify this matrix and this matrix? Okay. And again, fortunately, there are a lot of people who have done this work. Okay, and so there's, I'm not really familiar with those literature. So okay, so there are people with some, that doesn't have this W matrix, some has it, and so on. And a few people will actually have, instead of column sparse, you will have the various distributed data. Column sparse means that they only attack you on certain substations and not randomly through the network. Okay, so so there's some theoretical calculations and so on, and we can show that there's some analytical results that we can show. Certain subset that can be chosen, and the method will actually identify the channels that are being attacked. And you have noise, then you can get arbitrarily close. So this is the experiment that we did. So we have actual PMU data, and then and the red dots are the ones data attack. So they go through this. Okay, and what happened is that she and her graduate students were able to actually identify both. This is the ambient data, nothing is moving very much, and this is actually disturbance data, so it's moving somewhere. And they can actually identify which channel. So this is actually the list of channels, the column index, the list of channels. So she attacked the same channels with different things in it, and you can actually identify them. And disturbance detection with singular values. So if you look at a block matrix, if everything is steady state, you get only one non-zero singular value. The rest of them are actually pretty close to zero. So if at some point in time there's a disturbance, so there are variations between the channels, then you actually get more non-zero singular values. Okay, so this is the principle. So we can actually apply that. And so this is a particular voltage disturbance that we saw over here. If you and the window size, this is the important part, how long the data you want. Okay, so 3.33 seconds, and this is what you have. We only plot the second largest singular value, so you can actually see that it pops up. Okay, and then if you use a smaller window, you actually get sharper peaks. Okay, so you are more closely figuring out where the triggering point of the disturbance is. Okay, I won't go into detail of it, but one of the projects that we're doing is the voltage stability analysis with WinHub. So renewable energy is always very nice, But most wind farms tend to be integrated into a sub-transmission system, and there's only so much reactive power support and transfer capability in this. So some of these renewable integration, they actually lack the proper reactive power support, so a lot of the power transfer is voltage stability limited. Okay, so I'll skip all these things. This is the actual wind hub. And you can see that this is a picture of the voltage fluctuation in that wind farm as the wind starts to pick up. So this is about 10% variation, which worries the system operator very much. Wiring, monitoring, control, and one of the things that this is a diagram that we have for doing control with remote signals. So the idea here is that you have phasor measurement units in different parts of the system. But the nice thing about this is that everybody has the same GPS signal, so they can time tag the measurement. So when the measurement gets collected to a PDC, the control phasor data concentrator, it can be aligned. So even though they arrive at a little time later, you can actually align the data and be able to do damping control design. Okay, and this is the work that we actually do with UC Santa Barbara, because they actually have experts in switching control. Because eventually this is what we design. Okay, let me just stop here, and I will give these the slides to Professor Brattis, and then if you are interested,
I'll pass it.
you pass around, and don't worry about confidentiality, because most of those you can find it somewhere else over on the internet anyway.
Question?
Thank you.
I'm not sure how the GPS signal works, but a satellite up there puts a pulse out every second.
Yes.
And so you get it. Now, if
That's
you're
right.
reading a station in Niagara and you're only time delay, it's different between the satellite. It's got
Yep.
to go through more atmosphere, it's got a longer distance, it could be several milliseconds.
Yep.
How do you take that?
Well, it's definitely not milliseconds or seconds or milliseconds. Okay, I think that the signal arrival is the jitter on this is about 2 microseconds. I think the newer system will be 0.2 microseconds.
Well, I'm just saying, nanosecond a foot, 5,000 feet is 5,000 nanoseconds or 5 microseconds. Several hundred miles, that could be 500 microseconds.
I don't know how high those GPS units are.
Well, I'm just picking on 100, that's easy to.
Yeah.
But anyway.
In some
with respect to
geosynchronous
seconds,
orbit, right?
It's not a big deal with respect to seconds, but it may be irrelevant. You have to know what it is to say it's not a big deal. So I'm just curious, because I don't know how they, just simplicity thing.
Well, for these is simply the closest. I mean, the sampling signal. I think every satellite will send out something different. I mean, it's a signal. It probably had. Okay, I'm satellite 17. Okay, this is my second signal, and then your navigation unit will be able to tell, because you need multiple GPS unit for navigation. But for these guys, for these PMUs, is that whatever the first signal comes is good enough. Okay, and now, of course, a lot of these GPS signals focus on the U.S. So, and as a result, you don't need a very precise clock, which of course is money, right? In your PMU. So the U.S. standard is that you should be able to keep your time accurate enough for about 1,000 seconds. If you don't have any new GPS signal in for 1,000 seconds, you actually have to toggle the flag that actually notify the receiver, whoever that pick up the data, like the PDC, phasor data concentrator, that this particular PMU actually have an issue with the GPS signal. Now, the Chinese are very different, because the Chinese PMUs are much more expensive than the American PMUs. because they have a crystal clock in it. Because the specification of the Chinese PMU is that the Chinese don't want to rely on the American GPS system, but they don't have one yet. I mean, they probably have something, but not the complete.
There already.
They have already.
Beta. Beta.
Beta, okay.
Yeah, it's started to kind of operate.
Yeah. So the Chinese PMUs can operate without a GPS signal for, I think, a week. So what it means that you just have to buy a very expensive clock, a very accurate clock, which means it's an expensive clock. So who knows? I mean, the U.S. decided that it's probably not needed at this point. Okay, it can just rely on PMU signals, the GPS signals.
So there was a slide there that I think Ali Abour said that with PMUs you needed 1/3 of the measurements, and it really depends on the topology, but that's a rough estimate. Now, what are your thoughts for the distribution systems? I mean, where is the direction that we should go? Is it like aggregating information? Because we're not really going to get that number on the distribution level.
Well, I mean, distribution system is that you want
micro PMUs,
those micro PMUs, okay? I really don't know how it will go because the main part of these PMUs on the high voltage system is so that you can measure transients. When you are in a distribution system, I don't know how much transients that you're going to see, okay? And it has to be probably justified on different reasons, okay? That now, of course, distribution system operation is really not as sophisticated as transmission system operation. If you go to a distribution management system, or your company, or like over at our, we have National Grid as our distribution system operator. They actually have a control center, a much smaller control center, and they pull up maps of neighborhoods and so on. But their software are a little bit less sophisticated than power grid.
Isn't that a problem? I mean, a lot of the renewables nowadays, here in the state of Florida, solar, for example, they're going to be connected on that distribution system. And nowadays, they just don't have any state estimation on that. And the question is, well, to have a state estimator, if you have the micro PMUs and you consider the same 1/3 number, you will still need a bunch. I mean, in a distribution network, you would have a bunch of nodes. So what's the solution there?
Now, the distribution companies actually knows if someone actually installed rooftop solar, because they will actually put a dot on their map that you have rooftop solar as a map. And most of the rooftop solar is I mean, the rooftop solar tend to actually export directly into the line, and it's meter, okay, because you're actually going to get tax credit out of the meter, okay. Though I don't know how they want to handle it and how intelligent those power electronics equipment, how the power electronics interface to it, okay, and this would be a good question to ask to see how. Now, they are very concerned with this because every year the NYSERDA will have a meeting of the TOs. That every TO is going to present what they are doing with their system, and many of them will show a map of the number of the dots that they have. So the dots is actually filling up almost. They have to use next time they have to use smaller dots because the dots are so many that basically cover the whole surface area. But this is I think they worry about. Okay. I don't know what they can do for the time being, and in general, if you don't really have that many, I mean, but there are many, but they are not that big, so I think they can still do that for a while, but if you are in this research area, you have to sort of understand the future scenario, and this is the kind of things that they will be interested to hear from you.
A lot of people are talking about pseudo measurements, so measurements that aren't real, so they're based more on forecasts and things like that. But And the way they're sort of like getting out of that is changing the W matrix,
Mhm.
giving it a smaller weight or something like that.
Yeah, right.
But there's not really a standard, let's say, of which direction to go.
Yeah. Question?
Yeah, I have a question. I saw you list the one of the papers on the cyber attack, which is that would be the force data injection.
Right.
Some people are saying those kind of attack is not a kind of the real in the power system. What is your kind of
Okay.
study on that?
Well, I think most of the time, cyber attack means that the system operator is not getting the data. Basically, the data got stopped somewhere. Okay, and so we have people who study black hole attack and gray hole attack. Black hole means that you don't get data at all. All the data is blocked. Gray hole means that you get some data coming through, but at some other point in time, the data is lost. The intent of that is to cause disruption. Okay. I mean, again, you know, with missing data reconstruction, we can handle some of it. Okay. And if someone managed to inject bad data, but in a random fashion, we can take care of that. It's just like bad data detection. Okay, so you know, suddenly a data point is just out of whack.
Yeah, my question is because I'm coming from a networking side, and I know we are kind of working based on this assumption. Well, this is the data that can be injected this way. But what I'm asking, because I'm asking from the power side, whether it actually happened in the actual power system. That's my question.
I think that, I mean, the control centers are not any different from other computer installation in the sense that they are being attacked all the time.
Already.
But this is just like Target and, and Home Depot or whatever. And we decided that that is not the kind of attack that we like to be interested in about, because you really need truly computer science background and some additional system background and statistics background. But from the power engineer, the attack that we are most interested in are the ones that they actually can up to the point that they can do data substitution that we don't know about. Okay, and we need some additional techniques to look at that.
If I may just step in, there are some data that it's called critical data, critical measurement, where you do not have redundancy.
Okay.
So these are the most dangerous spots. What are these data? They're current, voltage, power measurements.
Yeah.
So if you can hack in there and actually make a change, substitute, there's no way actually you detecting that. You can't detect that even by the normal and the accepted methods, because there's no redundancy there. So they are measurements that are most dangerous. And these measurements usually are measurements from the field, power, current, and voltage.
So basically, this is a kind of the attack from the closer to the source, the measurement source. Right?
Yeah.
Because whenever you convert this into data, that this data that you're going to add a redundancy, whatever, line transport somewhere, right? So anything happen, and there's ways to detect whether there is attack or not. And in fact, sometimes I can kind of overcome this kind of the
Well,
substitution.
he could, for example, hack in and change that data.
Uh-huh.
And since you do not have redundancy, let's suppose that
Yeah.
the communication, the networks go everything fine,
Yeah.
and you're still processing the whole thing, but you don't know.
Yeah.
Because there's
Yeah.
no redundancy.
Now, we actually have not looked at the issue of critical data. Critical data, for those who don't know about it, is that if you lose those data in a regular state estimator, you actually lose observability of that part. That means that, as you said, there's no redundancy there. So those data, if you put in some bad data, those are very hard to, there's no way to detect bad data on those locations. Okay.
How difficult it is to kind of inject this data with that.
It's not very difficult, not at all, because you could do it two ways. Off the top of my head, you could do it. You can do it on the communications, meaning that you can have the right data, but then it has to go through the communications to get to the control system. So you can change it through there.
So that way you have ways to protect that. That's okay.
Well, then you can change it there.
Then you have to kind of penetrate the system.
Yes.
Yeah.
Yeah.
Get in there
That's
and change it.
Yeah. So that's why it's also the current the power system is connected to the internet. Use the public internet.
Yeah, that they are, I mean, this is probably true everywhere. So power system, they use, a lot of the power companies have their own proprietary intranet.
Yeah.
And the intranet may simply be part of a public internet. They reserve their own channels, so they actually have some isolation.
Really?
But a lot of the PMU data are actually broadcast out into the regular internet because there's much, you know, and let me back up a little bit, because suppose you have Enstar, which is a power company in Boston, okay? They have an intranet within the company, so the substation critical data goes back to the control center on that intranet. Now, the data that they send to ISO New England because ISO New England is not on their intranet, they actually have to use the public network.
Well, okay. That's
Okay, so this is what they have to do, and I don't know the exact detail of it, but I think it's whether they actually. I know that they have to pay for the bandwidth, and I don't know whether they have a security thing that they would like to do or whatever. Because once you go on the public intranet, then you have routers and other things, you know, and people can actually look at the traffic. So a lot of the things that another faculty has been looking at it is to look at what people are, you know, they're data watchers. So it's that they're people who just sit there and watch the traffic, okay? And I don't know what you can do, you know, but apparently they can figure out what kind of traffic it is, okay? The traffic analyzers, and then whether they would do anything malicious or not, I don't know.
the delay attacker, of course.
Yeah. No, I think it is, in terms of, you know, I mean, people do cyber attack because they want to do damage, right? And also to see where they can profit from it, okay? I mean, the most precious data that an ISO has are not the PMU data, but the generated bit data that's submitted by generators. Because those are data that another generator owner could figure out, you know, let's see how my neighbor bits, okay? And how I can undercut this guy, okay? Maybe I would underbid him just by a penny, okay? And then in that case, I would be dispatched, he wouldn't be dispatched, okay? These are the kind of things that you can actually make some money out of it. Trying to bring down a power system is probably not a very productive thing because you're not going to gain from it, okay? And right, I mean no, especially if you're not you're related to the insurance industry, you definitely don't want the power grid to go down. Well, thank you very much.
Thank you very much.
It's a pleasure.